Thanks very much. My name is Eckart. I work a little bit in the data center industry, those ugly dark buildings with no windows. And I thought I'd tell you a little bit of what's driving our industry, what's changing our industry. These are the topics that I'm going to cover in the presentation. And let's get straight to it. So really, we've seen some really rapid advances and lots of changes in IT infrastructure and server technology and networking technology, as we heard. And somewhere all of this comes together in a data center, so it affects us to a great degree because we need to provide the environment that obviously safely and securely houses these devices and provides power and cooling and all these wonderful things. So let's get straight to it. One of the big drivers are applications like high-performance computing. And up until 2 or 3 years ago, Donald, actually AI for me was all about artificial irritation or artificial illusion. I think hugely overstated buzzword in many, many forms. But it has now finally arrived in South Africa. So we are seeing some real AI use cases in the financial sector, in the health sector, insurance sector, agriculture. So AI has arrived on our doorstep, and it needs to be local. So as data centers, we're starting to need to deal with it. Now the hardware based on GPU technologies, as you know, GPUs, very powerful parallel processing devices with lots of processing cores, hundreds of thousands of them, drives power consumption. What's interesting, for instance, a few years ago, a simple Google search would maybe use 0.3 of a watt hour. Now, a simple chat GPT instruction is 10 times as much, almost 3 watt hours. And that's just very basic fun AI instructions, never mind more complex algorithms or graphic instructions. You know, so the power shoots up. The power shoots up to sometimes densities within a rack that used to be 3, 4, 5, 6 kilowatts a few years ago. Now we're being asked to provide up to 150 kilowatts in a rack. So those are tremendous amounts of power, and any power that you put into the equipment somewhere along the line, you got to cool it as well and bring it down again. So that brings the next set of challenges. And over and above that, GPU clusters are complex devices. They're made up of different server elements, data transmission elements, in between networking elements. So high-speed networking within our data centers also now takes center stage to make sure that data between the GPU and other devices can move freely and fast enough along. So first of all, rack power density. Here, for instance, you see some of the elements that we're starting to have to introduce. Power now is purely three-phase power just to cover the required loads straight into the racks. Here you see, for instance, a 42 outlet distribution unit, smart distribution unit, just to cover power consumption of all the devices in the racks. Sometimes we even need to put more than one of them just to cover loads of up to 150 kilowatts inside the rack. We also have some complex management systems around these devices because we need to carefully manage each of the outlets within the data center, within the rack. So just small fluctuations in power per any load obviously has large effect on our overall power consumption and power infrastructure in the data center. So the management of these power infrastructure devices gets a whole lot more complex. It's sitting in a real-time domain, but yeah, it's important to make sure that overall power capacity isn't exceeded to avoid outages or power trips or anything of that nature. Now, what we're finding with high rack power density as well, we're really reaching the maximum capacity of air cooling. About a year or two ago, these were still concepts that hadn't arrived, but now air cooling of anything above 25, 30 kilowatts a rack really can't be air-cooled anymore, so we're now having to introduce water cooling direct to chip. So this is essentially an additional layer of plumbing, essentially, that runs on top of the racks and brings in a feed of cold inlet cooling fluid, not entirely dissimilar to what runs in a motor car's engine, brings it all the way down through into the server chassis to a heat exchanger plate on the board itself, and passes out again as return fluid through an external sort of distribution unit at the end of the rack row that manages all the different water or cooling circuits out to a heat exchanger where that fluid is once again cooled and recircled back into the rack infrastructure. So essentially a closed loop cooling system that's now gets superimposed with a data center infrastructure, because we still need air cooling. We still have standard devices. We have different devices. We still need to keep the overall environment within a certain temperature range. So both systems have to now coexist in the same data center space. What's emerging as well now is that some of the OEMs that have already introduced the direct-to-chip cooling are now increasingly going to higher rack power densities. There's talk of rack power densities of 200, 300, even up to 600 kilowatts. Direct-to-chip cooling will also reach its limitations, and we're going to find that a new technology that has now emerged, which is called full immersion cooling. I don't know, has anybody has seen it here yet or come across it? We haven't seen it in South Africa, but some of the OEMs that we're coming across overseas are already starting experimenting with full immersion cooling. It essentially changes the way that the rack is orientated from vertical to horizontal, and servers are fully immersed in very specialized cooling liquids. But we expect this will for sure arrive on our doorstep as well in a few years' time. Now, network switching as well, our switching fabrics, and I think we heard quite a bit about network switching fabrics, so I don't want to spend too much time on that, but yeah, we are now seeing switching fabrics in our racks of 800 gigs. Network capacity, very high density, high power optical switches themselves that need to be liquid cooled as well. So network infrastructure equipment that was traditionally relatively low power consumption equipment is also now becoming very concentrated silicon-based photonics, generating high temperatures and requiring liquid cooling. Now, all of this is obviously an introduction of technology that happens over time and happens in different stages. It's not that we are going sort of just all of a sudden from 5 or 6 kilowatt racks to 100 kilowatt racks or something similar. So we're finding inside the data center, we're finding the need for really different infrastructure technology within the same area. And running of certain common infrastructure components. So because of the cooling, for instance, one thing that we've already diverted from is data centers generally now in the new modern design age no longer use centralized cooling system, but we use segmented decentralized cooling systems to be able to adjust to the different needs of the different types of equipment. One thing we found ourselves that serves us very well is modular and segmented data center architecture. So essentially that architecture allows us to segment the entire data center flow into small, what we call pods. And through the introduction of these pods, we can easily facilitate customized cooling, customized power distribution, or customized networking requirements. We're not only seeing changes inside the data center, changing the environment, we are also seeing changes outside the data center itself. Not so much yet in South Africa, but certainly overseas. And that really comes with the arrival of more and more low latency focused applications, real-time type applications, that is driving the need for a more distributed data center architecture. So this architecture essentially is used in real-time application, examples, for instance, self-drive cars, I think everybody's read about, we don't have them yet, but telemedicine, live monitored and managed electricity, utility grids, some financial applications whereby real life data needs to be processed rather at the edge, closer to the end user than in a centralized data center. So the edge data center concept is a concept where real life data is really processed and stored close to the end user, and in combination with back-end processing in a more centralized, converged, hyperscale data center. In South Africa, as I mentioned, we haven't seen much demand for this yet. I think we are pretty much industrialized around our metro areas only yet, so the latency factor is not so much of an issue. But I think as we're finding more and more real-time data applications coming into our daily lives, and as our networks grow more into the outer-lying areas, we're going to see more and more applications for a combined edge core data center infrastructure emerging in South Africa as well. And these are combined application scenarios. Sometimes people confuse edge data centers just because they happen to sit in a small town outside, but typically the workload determines that it's distributed across edge and core. Globally, what we're seeing is because of the large demand for data center power, utility grids no longer really coping with data center demands. A couple of countries, Ireland, Germany, Singapore, I think some instances in China I heard about as well, they're no longer approving data centers or battling to approve data centers because of the high amount of power that's required to run them. So data centers are having to make their own plans in terms of their own power generation. And this has led to some new power generation technology now being relooked at in the States now, in countries, APEC countries, Malaysia and so on. We're seeing data center projects reaching gigawatt stages, which is really quite huge. We're not, again, in South Africa, we're not there yet. But for that capacity, one of the technologies that's re-emerging is small modular nuclear pebble bed reactor technology. That is ideal. It starts with dedicated nuclear reactors, anywhere between 30 to 100 megawatts. And South Africa was, in the late 90s, actually one of the forerunners in developing pebble bed modular reactor technology. Got stopped because of funding issues, but it's a much safer technology. It's based on helium cooling rather than water cooling. Helium we have in the country, so we can easily accommodate this type of technology. It takes a long time for approvals and for design, plan, and build these projects. But certainly, even in South Africa, we have quite a few scientists, engineers that at the time were working on these pebble bed modular reactor technologies, and they are now busy developing technologies even for deployments overseas. Also, obviously, ideally for countries in Africa that don't really have utility infrastructure that works, and that don't really have data center infrastructure yet. So it's a new emerging energy technology that aligns very well with data center rollouts. What's facing us as well in the data center world is the drive for sustainability. As large energy users, as large users of scarce resources such as water for cooling purposes. We are seeing more and more demand by our stakeholders, by customers, by the investment community to move towards renewable energy sources, environmentally friendly energy sources, which is not an easy undertaking. The ones that we are seeing essentially don't provide for a stable base load. Solar and wind are good supplementary energy resources, but other energy forms such as biomass or waste to energy plants provide for better stable base load power supplies. But as data centers, one of our core topics is to procure as much renewable energy as possible, coupled to our self-generation, but self-generation needs a lot of space, and that's not always possible in the areas where data centers are built. Water utilization is also becoming very, very important, especially in South Africa. We are in a water-scarce country, so here we make use of systems like rainwater harvesting or obviously closed-loop cooling systems to minimize our water usage and optimize our water utilization factor. We're reaching numbers at the moment of half a liter or even less per kilowatt hour of IT load. So quite some good progress has been made in that field so far already. One of the areas that the European regulators are looking at and have started implementing is even the topic of waste heat regeneration. Scandinavia is leading in that example where data center operators are being forced to capture and bring back the waste heat into industrial or residential or commercial centralized heating networks, heating systems. In Germany, some of the later data center providers are being forced by regulators to bring up to 30% of their own waste heat generation back into their own heating requirements. So the reuse of waste heat is also another big area of development in terms of making data centers more efficient. So lastly, what is coming down the line for data centers are completely new technologies. Quantum computing, it's a very specialized, emerging area of quantum physics development. It really uses the principles of manipulating electrons into a computational technology that is substantially more powerful than our traditional electronic computing systems that we are used to. But again, it is a completely different environment because to achieve sort of modulation and changes to quantum physics elements like the electrons, it requires very complex environmental areas for the chips in terms of they need to be cooled down to near 0 degrees. That is achieved again through helium cooling. They need to be put into electromagnetically completely neutral fields to achieve electronics neutrality and stability. So what you see on that picture is really a complex array of a cooling cage as well as lots of wires and tubes that use either laser-based or microwave-based signal transmitters that change the behavior and program the behavior of these photonic or electron-based qubits inside that processor chip. But those applications are very, very niche in the area of biomedical research, in the area of drug research, in the area of astrophysics, very much a niche environment. South Africa is participating with a couple of programs through our university, KZN, Stellenbosch, WITS, all have quantum physics programs running through some of their faculties. IBM has sponsored some big programs with hundreds of millions of dollars where South African scientists are participating, but whether we'll ever see this technology implemented or brought to South Africa, we don't know at this stage. And that's all from me, just as a quick overview. So what's happening in our world? I'm not sure how many of you are involved in this. Any questions? Great. The man with no name.
Sorry, I'm walking slowly. Hi there, Dishal Gobradhan, no hats. Eckart, thank you, as always, because this is not my space. I'm fascinated by talks about data centers. They interest me because, well, I know nothing about building large-scale data centers. You ended on an interesting note for me. It's kind of the question I wanted to ask, which was, we don't know if this is going to take off. Today, I know that we're in data centers where sometimes they'll tell us you have 2 kilowatts of power per cabinet. Some of the newer data centers in South Africa are saying we can do 35, 40. I'm sure there's probably more, the data center space. But you said 160 and 400? Is that just vaporware? Is this like marketing the PowerPoint because it's on PowerPoint, it's going to work? Or are there actually data centers being built that's doing this? And my follow-up question to that is, are these like data centers where there's a data center and there's 2 cabinets in the data center and that's it, and there's like just space around it? Is that efficient for you as a data center operator to be building at that scale? Is it not? I know about the memory constraints and the timing constraints between RAM and getting things to the next AI, wada. But is it not easier for you just to say to spread your load amongst multiple cabinets rather than trying to push 400 kilowatts into a single cabinet? Asking as someone who doesn't know the stuff.
Yeah, no, it's a good question. I mean, power is the biggest overhead in a data center. Power is the biggest overhead for ourselves, for our customers. It is, unfortunately, reality. We're being asked for designs of 100 kilowatt plus, and it's really driven by the level of integration of large GPU-based, very, very powerful clustered systems that rely on a high density of thousands of processor cores, and you can't split them too far. You can run them maybe between racks of 1 or 2 cluster designs, but you can't spread them across a data center. So what you're finding is it's very specific applications, it's very specific niche workloads, but you have to accommodate them somewhere in your data center. And that's why I mentioned the strength of the modular concepts, because it allows you to segment small dedicated areas for very high power densities and different cooling technologies against all the other normalized or standard workloads that we're being used to. And if you build a data center, I think with 150 or 120 or even 100 kilowatt racks in mind, you'd probably wait for 10 years to fill it, and you'd go bankrupt in the process. So you've got to find ways to cater for the average demand, and the average demand, no doubt, is increasing all the time. But over and above that, you also got to cater for the extreme deployments of these high rack power densities. Okay, thanks.
Thanks, Eckart. So it was interesting that you pointed out, I think, at the beginning of your presentation, that AI just generating 100 words, costs a lot of energy. I saw an article the other day about being polite to AI is costing tens of millions of dollars by saying please and thank you. But what was more interesting about it is that it said a 2024 survey found that 67% of Americans said that they're polite to the AI assistants because manners